Hello and welcome to another video. In this video we're going to be working on greatest common divisor traversal. And in the problem you're given a zero index integer array nums and you are allowed to traverse between its indices. You can traverse between index I and j if the GCD of I and j is greater than 1, where GCD is greatest common divisor. Your task is to determine for every pair of indices, is there a sequence of traversals that can take us from I to j. Return true if it is possible to traverse from every single pair of indices. So in this first example, we have 2, 3, 6, and they say it is possible to traverse because the GCD of 2 and 6 is 2, so you can traverse from 2 to 6 or back because it's greater than 1, and you can also traverse from 3 to 6 and back because the GCD there is 3. So because you can traverse from these points to 6 and back, you can traverse anywhere to anywhere. So like if you want to go from 2 to 3, you just go 2 to 6, 6 to 3. And if you want to go 3 to 2, similarly 3 to 6, 6 to 2, and 2 to 6 or 3 to 6, there's a direct traversal. In the second example, there is no direct traversal. You can traverse from 3 to 9, but you can't traverse from any of them to 5, so you return false. In the third example, there's a bunch of traversals, so any even number, you're going to be able to traverse from one to the other, so we can actually draw this as like a graph. So we have 4, 3, 12, 8. Any even number is always going to be connected because the GCD of two even numbers will at least be 2, right? So this is connected, this is connected, this is connected. And then from 3, you can traverse to 12, right? Because the GCD of 3 and 12 is 3. So this whole thing is connected. You can traverse from anywhere to anywhere. So that's kind of the idea from seeing these examples is, in order, if you have two numbers, let's say we have like 12 and 4, or even not even like 12 and 4, let's say 12 and 8. When you're looking for, we don't really actually care about the GCD. We care about more, is there a factor that both of these share that's greater than 1? And if there is, then the GCD is automatically greater than 1, right? Because if we can find one factor, the GCD is the greatest common factor. So by definition, the GCD will automatically be bigger than 1. So if we find a factor for these two, like 2, like these can both be divided by 2, that means the GCD has to be at least 2, because literally, if there is no other factor, then it will be 2. If there's something better, then we'll return that. That's kind of the idea. Between two numbers, we can just find a factor of greater than 1, and if there is one, then we can return it. And similarly, we can also only look for prime factors because, like, let's say there's some factor that's non-prime. Let's say the GCD is non-prime here. Let's say, so here it's actually 4, right? Well, if we find a prime factor, like 2, the GCD will either be this, or it will be a multiple of this, right? So it's going to be easiest to find prime factors. So basically, we can just get prime factors of both of these numbers, and then check, is one of them shared? So like the prime factors here are 2 and 3, and the prime factors here is just 2. And we can say like, oh, there's a 2 and a 2. So the GCD will be, might have a 2, might not. Or I guess it has to have a 2 by definition, right? Because the GCD will have to contain a shared prime factor. And so it might just be bigger than this, which it is. In this case, it's 4. But that's always the case. So similarly for like 15 and 25, the prime factors of 25 are just 5 and 5, so just 5. And 15 is 3 and 5. And the GCD, if there's only one shared prime factor, will have to be a multiple of this factor. If there's multiple shared prime factors, then it can be like a combination of them, obviously, right? But yeah. Like let's say we have like 6 and 18 or something. The prime factors here is 3 and 2, and the prime factors here is 3 and 2. So that's why you can have like a combination of them, right? Because they're both shared. But the idea is, given two numbers, if we can find one shared prime factor, then we know for sure the GCD is going to be greater than 1. But like, what would be the brute force here? Like let's say we have 4, 3, 12, 8. We can't just take every pair of numbers. We can't just be like, okay, let's take 4 and 3, find their prime factor, see if there's a shared factor. If there is, let's connect them. Because getting the prime factor of a number is somewhere around log n or square root of n. So to do this, like if we say like, okay, for 4, 3, let's find prime factors. For 4, 12, let's find prime factors. For 4, 8, let's find prime factors. Even if we like, obviously we could be like, hey, let's just actually get the prime factors ahead of time, right? So we'll get some factors here, some factors here, some factors here, some factors here. And then we can like compare them for equality. You still have like a bunch of numbers here and a bunch of numbers here. So this is not like even if this was O of 1, right? Like even if you can get all the prime factors of a number in O of 1 and compare them in O of 1, it would still take too long because comparing every index to every other index is n squared, even if the comparison takes O of 1 and the prime factors take O of 1. But in this case, it's not. So instead, what we can do is instead of comparing the actual numbers, we can actually just compare the factors. So what we can do, just to go through this example, is like for 4, first of all, we can get the prime factors. And I'll talk about like efficient ways to do that. So for 4, the prime factors are like 2. For 3, the prime factor is just 3. For 12, the prime factor is just 2 and 3. And for 8, it is just 2. Then we know that if numbers share a prime factor, then those can be connected. So like if 4 has a 2 and 8 has a 2, that means their GCD will be greater than 1. So if numbers share, they can be connected. So instead of having the key be the node and having the value be a list of prime factors, we can swap that around. So our key can be the prime factor. So for like 2, what nodes do we have? So 2 is node number 4, node 8, node 12. And then for 3, we have 3 and 12, right? So you could see like 4, 8, and 12 have a prime factor of 2, and 3 and 12 have a prime factor of 3. Now that we could do this, all we have to do is just connect every node in each prime factor. So everything that has a prime factor of 2, we can connect it. And everything that has a prime factor of 3, we can connect it. And what's that going to look like now? So we'll, like when we actually look at our nodes, so we'll have 12 goes to 8, goes to 4, and then 12 also goes to 3. And then we can just like BFS from any starting node. And if we BFS from any starting node, we should be able to visit every other node, right? So that's like the better way of doing it. Instead of going by node and its prime factors, we go for the prime factor, and then we connect every node in the list here. And the easiest way to do this is also going to be, you can do it this way, but you can actually just use union find, because it's like perfect for union find. So you can either store the values here or the index of the actual number, right? So 4, 8, 12, you can either store 4, 8, 12, or you can store the index, which would be 0, 2, and 3. And that's what I'm going to end up doing. So we're going to have 0, 2, and 3. And then for 3, the things that have 3 are 1 and 2. 1 and 2. Then you just literally go through every 2 adjacent numbers, you union find them, and a union find will just connect them into a component. So like this will be a component, then this will be connected, so this whole thing will be a component, and then when we connect 1 and 2, this whole thing will be a component, right? So then we can just check, like, okay, at the very end, how many components do we have? And then we should have only one component, right? Because everything should be connected. Now, the key thing to this problem is, okay, so we can go through every number and we can get like the prime factorization. And then we can go through for every prime factor, we can go through all of the numbers in there. Like that's fine and that does work, but we have to have an efficient way of getting prime factorization. Because, like, let's just ignore this part altogether. If we just go through every single number and get the prime factorization, there's 10 to the 5th numbers. So you need a way to get the prime factorization in log n or better. And it turns out you can actually use the square root factorization that I have in my prime factorization video, and that will actually work. So the average, the worst case time complexity for a prime factorization using the thing that I have up that I'll briefly describe is root n, but because for most of them it's going to be significantly faster, on average it'll be like log n or something, and then it will pass. So because like root 10 to the 5th is like a little over 100, it'll be fine. It'll basically like barely pass. And the way to do that, I'll show you 2 different ways of doing this. The one video I have, and then there's another way that's a little bit more efficient. So let's say we have like a number like 123, or let's just pick a number that we know. I don't know if 123 has factors. Let's say we have like 135. The way to do this efficiently, like reasonably efficiently, like the worst way to do it is literally loop from 1 to 135 and then see if you can divide your number by that and keep doing that, because that will be an O of n prime factorization, and that will definitely fail. So a more efficient way is knowing that if I have factors that aren't just the number and 1, then one of those factors has to be square root of n or less. Reason being, let's say we have a number that is a perfect square. So let's say we have like, let's just think of one that's reasonably big. Let's say we have 81. So 81 is a perfect square, and two factors are 9 and 9. Well, these are both root n. And if we increase one, that means we have to decrease the other for them to be 81, right? There's no way around that. So you're guaranteed, if you have two factors, if one is greater than root n, then the second one has to be less than root n. So that's why you can just go through numbers root n or less, and we're just going to find the smaller factor, right, all the time. And then if we find the smaller factor, we'll divide our number, and then we'll get like another smaller factor, and so on and so on. So for 135, let's just go through how this would work. So we're going to start at, like, the first factor we'll start at as 2, and we'll just keep going up until root 135, which is roughly, so root 144 is 12, so we'll just go to like 12. So we'll go from 2 to 12, and we'll see like if we can divide anything. So obviously it's not divisible by 2. Is it divisible by 3? It is. So yeah, it definitely is. So it is divisible by 3. So in 3, we will put our number, right, like 135. Because that is a prime factor. 3 is a prime factor of 135. Then we're just going to divide 135 by 3 as many times as we can. So if we divide it by 3, we get 45. And then we see, like, can we divide 45 by 3 again? Yes, we can, right? We can get 15. And can we divide 45 by 3 again? Yes, we can. We can get 5. So basically, our number is just like 3 a bunch of times, and then we have 5 left over. Now we can't divide 5 by 3 again. We're only trying to get like actual integer values. So then we go to our next number that we try. So we tried 3. Now we'll try 4. Is 5 divisible by 4? No, it's not. Then we'll try 5. Is 5 divisible by 5? Yes, it is. So for 5, we will also put 135. And now when we divide it, we will get 1. And then once our number is 1, we can't like get any more prime factors, so we're done. So essentially, the code is something like loop from 2 to square root of number. See if the current number is a factor. If it is, divide number by factor until we can't anymore. And break loop when number is 1, right? So that's kind of the idea, and you can do this for a bunch of numbers. So we can do it for like one more number really quick, I guess. Let's just make sure it actually has, it's not prime, I guess. So let's pick a number like, let's see, 237, I guess, is like not prime. So we're going to kind of do the same thing. So first we take 2. Is it divisible by 2? No, it's not. Is it divisible by 3? Yes, it is. So we're going to put it in here. And 237 divided by 3 is 79. Then is it divisible by 4? No, it's not. Is it divisible by 5? No, it's not. 6? No, it's not. 7? No, it's not. 8? No. 9? No. 10? No. And I believe 79 is just prime, I want to say. So I don't think it's divisible by anything. So basically you're going to get 237, or you're going to get 3 as a factor, and then you're going to get 79 as a factor. So for 79, you will add it in as well. And then you'll basically just be done. And yeah, and like we won't have to check all the way up until 79. We're only going to check up until the square root of our original number. So for 237, I don't know, this is exactly, I think this is like 15 rounded up or something. So we're only gonna try 1 to 15, and then when it fails for 15, we know this has no more factors, because like I said, I think 15 times 15 is like 225 or something. I could be wrong, but around there. So basically, if one of the factors goes up, let's say it's like 16, then the other one has to go down to something else. So we know for sure if we just try only 1 through 15, that means this has no more factors. And then we can just, yeah, so that's like one way to do it. And this is like worst case, square root of n factorization, average case, log n. Now the better way to do this is called like the sieve of Aristophanes. I'm not sure if I pronounce it correctly, but essentially, if we go back, we can just try, the way this works is we look at our biggest number that we have here. So we have 12. So we can build an array, and let's show this. So we can build an array up to 12. So we have a couple more here, like this. Hopefully, whoops. Let's put this. Okay, there we go. So we'll build an array up to 12. And the way this basically works is everything will be initialized to 0. So I'm just going to have a blank space, meaning 0. And we're going to start at our smallest number. And then anytime something has a 0 value, that means it's a prime number. So everything will be initialized to a prime number. 0 and 1 will obviously be prime numbers, right? Because, or I guess they're technically not prime. There's like some other word. But essentially, 0 and 1 will be like 0, and then we're going to start over here. So we know for sure that 2 is a prime number. So basically the idea is for every number, if it's a prime number, we are going to keep adding that value and then check, are those numbers prime as well? And if they were prime before, then we're going to, essentially the goal here is to find the smallest prime factor of a number. So initially, everything is going to get defaulted to 0, which means the number is its own prime factor. You can't have everything defaulted to like the actual value it has. So you can write like 0, 1, 2, 3, 4, 5, 6, 7, and so on if you want to. But I'm just going to say 0 is going to represent the number is its own smallest prime factor. So let's show how this works. So we know 2 is prime for sure, and 2 is its own smallest prime factor. So we're going to write this as 0. Then we are going to keep adding 2 until we get to the end of our array. So we're going to add 2, we're going to go to 4, and we're going to check, okay, if 4 is its own smallest prime number, right? Like if 4 has a 0 in here, which in this case it does, that means that 4 is not the smallest prime number because we got from 2 to 4. So from every number we get to from 2 that is its own smallest prime number, we're going to replace it with 2. So we get to 4 and we're going to say like this, and we're going to say, now this is 2. Then we're going to go to 6, this is 2, 8, 2, 10, 2, whoops. So this is 2, 2, 2. Then we're going to do the same thing starting at 3. So we're going to say, and by the way, so we're only going to do this like populate up if a number is its own smallest prime number. If it's not its own smallest prime number, that means we got to this number from some other number. That means this can't be like the smallest prime factor of something. So here, what we're going to do is, yeah, for 3, it is its own smallest prime number or prime factor. So we're going to populate up again. So we're going to go up here and we're going to say, if this doesn't have a value, we'll change it, but it already does, so we'll leave it. Then we're going to go up to 9. 9 doesn't have a value, so we'll put 3 here. And then 12, and 12 does have a value, so we're done there. Then for 4, 4 already has a value, so 4 is not prime, so we can just skip it. Then 5, 5 does have a 0, so we're going to do this populate up again. So we're going to go to 10, 10 already has a value, so we're done. 6 is not prime, so we skip it. 7, we can do 7. So 7 is 0, and if we try to go up, we'll be out of bounds, so we're done. 8 is not prime, 9 is not prime, 10 is not prime, and 11 doesn't have a number, so 11 is its own prime number. And these are the results. So you can see like 2, the smallest prime number in 2 is 2, smallest prime number in 3 is 0, smallest prime number in 4 is 2, 5 is 0, and so on. And so now, the reason this is good is because our previous approach, like once we found a prime factor, we have to kind of like keep increasing our number. So like in this 237 example, we did find a prime factor. It was 3, but then the second one we had to go through a bunch of values. We had to go all the way up to 15 because we didn't really know like what was the next prime factor. But now that we're going to fill out this array from the smallest to the biggest number in our array, now let's say we have like 10 or something, and let's say we have 10 and we know that like its smallest prime factor is 2. So we can divide 10 by 2, we get 5. And now we know right away what's the smallest prime factor in 5 just by looking at this array. So once we get a prime factor, we can immediately get all of the prime factors. Like once we get one, we can get the next one, next one, next one, and O of 1. We don't have to do this like iteration process. We're actually just filling out like for every single number what's the smallest prime factor. And then when we have some big number and we divide it, we'll just have another number and we can just do a lookup like what's the next smallest prime factor, and we keep doing that and we keep doing that. And that's going to be more efficient. But that's essentially the two ways of doing this, and this is called like the sieve of Aristophanes or something. And this is more efficient than the just the square root prime factorization. But the brute force prime factorization will fail, the square root prime factorization will barely pass, and this one will pass with better time. So I think this is like log n or something to get all the prime factors of a range. And because the biggest number in the here is 10 to the 5th, that'll be fine. Like that's what this depends on. Like what's the biggest number? And also because there's 10 to the 5 numbers, worst case, and there's 10 to the 5 numbers, worst case, you're just going to be like, you're gonna save a lot of time pre-computing this thing when you are getting prime factors. So yeah, so let's take a look at the code now. I'm going to show you both ways of doing it. So both of them are going to use a union find, and I added one tiny thing into the union find. So I added a components field, and that basically is going to be initialized to n. So let's say we have like 4 components. Like let's just say in the beginning we have like 4 nodes, like 1, 2, 3, 4. Well, that means we have 4 components, and every time we have a successful union, I just subtract 1 from the component. So like if we have a union here, our components will be 3. If we have a union here, components will be 2. If we have a union here, components will be 1, and so on. So every time you have successful union, and in union find, you can only have a successful union if your components were not connected already. So if everything is connected at the end, you'll just have 1 component. So that's what I did here, just a standard generic union find. And then let's take a look at the prime factorization with just the thing I was saying, the square root approach. So we make a union find, we make a primes dictionary. We go through all of our numbers. For every single number, we get all of the primes. We get all the prime factors. And then for every prime factor, we basically just append the number we're at. So then we end up having a dictionary of all the prime factors and all of the... So I put in the index here. You can put in the number. Either one works. So yeah, I put in the index, you can put in the number. As long as the numbers are unique, which I think they are, it's fine too. So essentially we can even print this. So just to show you an example, so we can actually just say like print primes, and we can run it really quick. And you can see that like, here's an example here. So you can see that like for a prime factor 2, index 0 and index 2 both have a prime factor 2. For prime factor 3, index 1 and index 2 have that. And now, once you have this, essentially for every single list, you just connect everything in the list. And because you're using union find, all you have to do is connect adjacent elements. You don't have to do like, to connect n elements in union find only takes n connections. You don't need n squared. And so that's why it makes it faster. So let's go back to the code. Yeah, so this is what I did here. So essentially, we just go through every single array in our dictionary. We don't really care about the keys, but we care about like the actual values, right? So every single array of values, if we go back here, you can see that like, these are the things we care about, right? So for every prime number, every single array of values, we're going to connect all of these. And that's what we're doing here. So basically you just go through all of the, so each val is an array, and then you just connect every adjacent element, which is fine. With just a normal union, then you just finally return how many components you have. And so we can run this with just a standard prime factorization. I was trying a bunch of other edge cases. And you can see it works, but it's a little bit slow. But a lot of solutions have this, I'm guessing. And now we can comment out this one and show the sieve of Aristophanes. Sounds kind of funny. So here it is. First of all, what we do is we get the max number in all of our numbers, and then we compute the smallest prime factor for every number up until that number. So we initialize everything to be its own smallest prime factor, giving it a 0. Then we loop from every number from 2 on. We just say, okay, if this is not a prime number already, then we can skip it. Otherwise, we are going to keep adding this number to where we're at, right? Like I showed you before. So if we're on like 2, we'll go to 4, 6. So whatever number we start at, we'll keep adding that. So if we're at 5, we'll go to like 10, 15, and so on until we get out of range. So we keep adding that number, and then we check, is the number we're on its own prime factor? If it is, well, now we found a better factor. So we're going to update it to that. And then essentially we can also print this just to show you what this is going to look like. So if we print this sieve, so here it is for 2, 3, 6. So this is going to have every number from 0 to 6. So 0 is its own prime factor, 1 is its own prime factor, 2 is its own prime factor, 3 is its own prime factor. 4, the smallest prime factor is 2. 5 is its own prime factor. And 6, the smallest prime factor is 2. So this is basically what you have. And now you can get prime factors of any number in O of 1. So you build it, then you do the rest of it is the same. So we go through our numbers, but now instead of manually looping from 1 to square root of n, we just say like whatever number we're on, let's just get the prime factor. And we can look it up. If it's 0, then it's the number itself. If not, what's the number there? And we'll just use that. So we can get the factor, like the next, the smallest prime factor of any number in O of 1 once we compute this ahead of time. Then the rest of it is all the same. You just get a factor. You keep dividing your number by the factor as much as you can until your number is 1. Once your number is 1, then you're done. Then same thing literally as the thing above. For like, we can even show this again. So we can print. We can even print, we can print primes here one more time, and we can look at like a couple things. So you could see like basically the values in this primes is just going to be all these arrays. And so for all these arrays, just connect every element in each array. And then finally at the very end, you just have to check how many components do you have left. So union find is pretty flexible. Some things I found I'll briefly mention. You can have this components, really easy to add. Another thing that you can do that is pretty useful is sometimes you want to check like one other way to do this is you could go through your roots, and when everything is in the same component, every single root of every single element will be 1, right? Because you have one component, so everything will have the same parent. So that's another way of doing it. You can also like do other things like in this find, make like a dictionary or something, or use this find by itself, right? There will be times where you actually need to look up like what's my node and what component is it in and what's the parent there. So I have used like find just by itself before. Normally for like 90% of problems you just use union, and union calls find, but you can use find to figure out like what's the top level element of my component, and then like use this roots array to build different components and see how things are connected. But yeah, so we can run this, and you can see it's like significantly faster, and this is like the better solution. But this one's kind of hard to come up with, and you might think that for a normal prime factorization it'll fail. Like I said, it's kind of close. I think LeetCode fails around 10 to the 8th or so. So because the average case prime factorization using the square root one is still log, it's still fine, but barely passes. Yeah, so we can go through the time and space. For these, it's definitely hard to come up with these things correctly. So hopefully I do, but probably not. Okay, so let's take a look. So to build up this sieve, it basically depends on the biggest number in your array. So obviously, like the sieve won't be very good. It'll be better to just go number by number if, let's say, you only have like 10 numbers, but your numbers are really big, right? But here we can have a lot of numbers. So maybe like the best solution will have like a, you can check how many numbers are in here. And then once the number of numbers is a lot, you use a sieve. And if it's small, then you just use the normal prime factorization. And so, yeah, the time here is going to be, so to build a sieve is like log, or I think it's like actually n log n, where n is like the biggest number here. So we can call this like max num or something. Something like this. It gets kind of complicated for the time to actually like figure this out too, like to prove it or something. You can look it up on Wikipedia. I'll probably just provide a link for you. And then union find is all O of 1 operations. So for every number, you'll have at most, like you'll only have each thing once, and there's not that many primes. I think there's like 1,000 primes or something, or less. We can probably look it up actually, so we can look it up primes. Be under 10,000. So let's see, or number of primes maybe. Yeah, so there's only like 1,000, so there's not that many. But yeah, essentially, for every prime, you'll have some elements. Obviously, it's also pretty rare. Like for the super rare primes, there's not too many elements with them, right? Like, you know, primes like 2 whatever, or 131, or all those like weird ones. So the majority of numbers just share like the really small primes. So like I said, it's kind of hard to know exactly how fast this runs, But essentially, yeah, for every prime you can have, worst case, every node, but you really won't have every node, and there's like 1,000 primes. So it'll technically be worst case, like technically you might think worst case it fails, but it still passes, because if there's 1,000 primes and every prime has every number, then it would fail, because that would be like 1,000 times this, but that's not the case. So I think I'm going to write this as like number of primes times n, where n is the length of this thing, but I think in reality it'll be a lot less, because if you think about it, like it's very rare for a number to be made up of a ton of primes. So in reality it's going to be way smaller than that. That's why it'll work. And yeah, I think it's going to be all for this one. So thanks for watching, and I'll see you next one.